Okay, so this is Math 331, Lecture 12. So this is the second part of today's lecture. We're going to continue our work on the pigeonhole principle. And then we had just done a little bit of work on monovariance, which is the other topic of today. So we will do more on both of them. These are two of the really big problem-solving techniques. The pigeonhole principle is more known than monovariance, but they're both worth seeing. Okay, so the first is, let's see, we should probably do another pigeonhole principle problem just to get comfortable with the method, and then see what you could use it for theoretically. So let's do the following. Example. So let's see. Take S to be the numbers 1, 2, 100. Choose 55 from S. Claim at least 2 differ by 10. What do you think would be useful? I have to do this with a straight face. What do you think might be useful to solve this problem? Interesting. Yes, it's the pigeonhole principle. What numbers do you think are really important? Yeah, 55 is probably important. What else? What else do you think matters for this problem? 10 and? So the question is, what's the relationship between 100, 55, and 10? If I were to scale this, if I were to make this 10,000, what would you expect that to be? Is this 1/10 of that? Is it the square root of that? What's really going on? Why 55? So how might you try to come up with a... So one possibility is to see, instead of just trying to solve the problem, let's build some intuition. Can you come up with a set that doesn't have any elements that differ by 10? So sometimes it just helps to build intuition, because we need to, for pigeonhole problems, we need to identify two things. What are the pigeons and what are the boxes? Let's try to get some intuition as to what these sets could look like. So let's look for sets that fail the conclusion. Now, these sets should not have 55 or more elements. Anybody want to give me a possible first set?
We can have 1 and all numbers mod 3 modulo 3 with remainder 1. So 1, 4, 7.
Oh, so you're going to go from 1 all the way up to 100. You're going to count by threes?
Yeah.
Okay, so 1 is to go from 1 to 100 counted by 3. So it's 1, 4, 7, 10, 13, 16, 19. Wait a minute, am I making a mistake? No, I'm fine. 22, ... and I would end with 100. Right? So how many elements does this have? So size is approximately 33. I don't care if it's 33 or 34 or 32. It's around 33. Okay, so good. This gives us a nice structure. And then you're using the fact that with multiples of 3, they're never going to come up to something that's 10. So now the question is, could we actually fill this in a little bit? We could probably fill this in a lot. Yes?
Just to clarify, is the claim that two adjacent members can't differ by 10, or just any two members?
Any two members. At least two members of the set.
So how does this fail the conclusion?
Well, give me two numbers whose difference is 10.
Oh, by exactly 10. Okay.
By exactly 10.
Okay, sorry.
Right.
Okay, yeah.
Sorry.
Never mind.
Yep. So we could start filling in this a lot. So there's another way to construct a counterexample, or to construct a set. It's to use the greedy algorithm. So we saw this just a few moments ago when we were looking at the Zeckendorf decomposition. You start with the largest thing you can and you keep going. So what number should we start with? You know, I want to start choosing my set. What should I make my first element of the set? I'm sorry? You could start at 100 and work down, or you could start at 1 and work up. It really doesn't matter. I like working from the bottom up because it's less chalk. So we're going to do things greedy. Hey, you know, I got to have money to buy these munchkins, right? So what could we add after 1? We could add 2. And then we could add 3. What's the last number we can add greedily? 10. What's the next number we add after 10? 21. 22 all the way up to 30. And then what comes next? 41. 50, right? And then we would skip 50 to 59. Can't do 60, can do 61, 62, all the way up to 70. Can't do anything from 70 to 80, but can do 81, 82, 90. And I don't think we can do anything else. So let's see how many we get. 10, 20, 30, 40, 50, I think. Size of 50. So actually, maybe 55 is a little bit excessive. Maybe we can do it with less than 55. Sometimes it's nice to just give yourself a little bit of freedom when you're lecturing at the blackboard. Can anybody think of another approach that might lead a really good rich set? So I like the idea of starting with every third, because we know no multiple of 3 will ever be a 10. And then we can start filling things in. We could easily fill in a 2. We can't put in a 3, so we could add a 2. We can't add a 3. Can we add a 5? We could add a 5. We can't add a 6.
You could just add, you could just do the cycle of 3 again, starting at 2.
That's what it's looking like, isn't it? But is that going to cause a problem? Because that would give us over 60 elements. So if we would want to say, can we add 8? And then what would come up over here? Which we can't add because of the 1. Whew! Okay, right? Things are good. Because if we could have just done that full cycle, we would have had trouble. We would have had over 60 elements.
Because then because if you'll have intervals of 8, or you'll have intervals because you have 3 times 3 plus 1.
Exactly. And so then it's a nice question to ask, how many of these numbers could you add? Maybe we then have to just rest for a little bit and then start adding them again. Oh, that seems very similar to this. Add a bunch, rest. Add a bunch, rest. So again, the greedy idea is very nice. You can also start with the set and then see what can you do to it. Okay, so this is a nice description of some examples. Now that we have some ideas, let's try to figure out for this problem, what are the pigeons and what are the boxes? And the chalk just broke. I'm holding it very carefully so you might not be able to tell, but it's dead. Okay. What do you think is easier to identify, the pigeons or the boxes? Pigeons, right? It's very hard to disguise what the pigeons are. What are the pigeons for this problem? Yeah, the 55 numbers. The 55 elements or numbers. Now we have to figure out what are our boxes.
Like the 1, 1 plus 10, 1 plus 20.
Yeah, let's look at the numbers mod 10. You know, we've got a 10 here. Let's look at things mod 10. So box 1 is going to be 1, 10, I'm sorry, 1, 11, 21, 31, 91. Dot, dot, dot. Box D is going to be D, 10 plus D, 20 plus D, 90 plus D. So how many boxes do we have? We have 10 boxes. What's the first box we should have done? 0. So we also have box 0. We should be a little bit careful. And I'll write it as 100. Or I guess I'll put the 100 at the end. So it'll be 10, 20, dot, 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 100. So all boxes actually have the same number of elements. So we have 10 boxes of 10 elements. We have 55 pigeons. What can you conclude?
At least one box has 6.
So one box has 6. So at least one box has 6 numbers. For this argument, do we need 55? Why do you think this problem was given with 55? I think it's only a guess. I don't know who made this problem up. Yes?
Maybe 51 would make 50 very obvious, like, limit.
So one thing is sometimes to disguise things, right? A lot of times you put in red herrings. And if you put in something like 55, it makes things look a little bit more complicated. That is definitely a technique people do when they write problems. Another which I'm thinking is that 55 divided by 10 is 5.5, which rounds up to 6. If you did 51, 51 divided by 10 is 5.1, which rounds down to 5. You shouldn't be rounding down to 5. If the average number of pigeons per box is 5.1, each box can't be 5 or less. Because it's an integer valued quantity, it has to move all the way up to 6. So there is some nice consequences of being an integer. How many of you have taken complex analysis? Okay, if you want to go to grad school in mathematics or physics, I strongly recommend you take complex analysis. One of the big things you learn in complex analysis is something called the winding number. And it's often a continuous function and integer valued. What can you tell me about a continuous integer valued function? So f of x is always an integer, and f of x is continuous. It's constant. We really understand constant functions. And so this is a real nice benefit of knowing that something is integer valued. So now we know at least one box has 6 numbers. So without loss of generality, which box do you want to assume? Yeah, I think the 10, 20, 30, I think this is the nicest box to work with. So we've got to have 6 numbers out of here. So we have 6 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have to choose 6 out of 10, such that you don't have 2 touching each other. Is that possible? No. Now, how rigorously do you want to prove this?
Pigeonhole again.
So can we do pigeonhole again? Could this actually be a double pigeonhole problem? So how would you do this?
Well, we can do 10, 20 in box 1.
Yep.
30.
This is a double pigeonhole problem. It's unfortunately not twice as much fun. It's only like root 2 as much fun. It doesn't grow linearly. but it's still fun. Okay? It's a double pigeonhole. What is the only thing that might be better than a double pigeonhole? A triple. And then you dare to dream the n-dimensional pigeonhole problem. Okay? So now we have 5 boxes. And one of those boxes must have at least 2. So 5 boxes, at least one gets 2. Done. We could have also tried to do it directly. Case 1, we could do it by induction. It's clearly true if we have maybe start off with 3 out of 4, right? And then show that if we have 3 out of 4, it works. If we have 5 out of 8, it works. And then in general, if I start off with this one over here, I can't have this one over here, and now I've reduced it to a previous problem. Or if I don't have this one, and I don't have this one, it's even better. Or if I don't have this one and I have this one, then I don't have this one, and again, I'll be fine. So you could also do it by induction. The induction, I think, is much harder. And so I would much rather do a double pigeon. Okay. Anybody seen Monsters University? I'll try. Okay. So in the beginning of the movie, when they're going to Monsters University, you actually see a pigeon, going down on the ground and eating some stuff. And it turns out that the pigeon actually has 2 heads. So that would be a really good, image for this problem. Okay. So applications. So this is a problem-solving class, but we're developing techniques. And the question is, why do we care about these techniques? What can we use these techniques for? So there are certain mathematicians who have far too many theorems attached to their name. And if you say, Gauss's theorem, you have to ask, well, could you please be more specific? Dirichlet is another one, and we're going to do a theorem from Dirichlet. One of my favorite mathematicians is Chebyshev. How many of you have ever seen a theorem by Chebyshev? If you take a stats course, you might see, or a probability course, you might see Chebyshev's theorem for the probability that just so many times the standard deviation away. The reason I love Chebyshev is there's at least 50 different ways of translating his name from Russian to English, and I'd like to use a different translation for each theorem, so that depending on how you spell Chebyshev, you could immediately know which of his theorems you're referring to. I have yet to get the mathematics community to support this. But maybe Dirichlet's approximation theorem. How many of you have gone deep in computer science? Anybody? Okay, so 2 people, excellent. So all a computer can do essentially is manipulate zeros and ones. All the computer can do is deal with finite combinations of zeros and ones. You can only attack rational numbers. So if I want a computer to attack a number like pi, I have to somehow do an approximation to pi for the computer to work with. And so a natural question is, how do I find good rational approximations to numbers? So Pi Day is fast approaching. There will be a colloquium the day after Pi Day that will be talking about some interesting ways to approximate pi. Can someone give me pi to a couple of digits? Is it 535?
I know it's 897 after that, but I don't know if that's the 5.
I'm pretty sure it's a 5. We'll assume this is correct.
897.
Oh, sorry. Yeah, hold on. That would just be a strange world. Right. Okay. And then there's a great debate between Professors Garrity and Adams as to which is more important, pi or e. In complex analysis, you see lots of evidence for pi. There are some people who actually say the correct constant is not pi, but 2 pi. Because you have 1 over 2 pi occurring in so many things. That should be your fundamental point of view. There's a very small minority of people who actually say 4 pi. Actually, I don't know if they exist. I just say that they should exist. Because how many of you remember Gauss's lemma and these divergence theorems? You have 1 over 4 pi epsilon naught from physics. You have the surface area of the sphere. And so for a lot of things in physics, 4 pi is the one that really matters. For us, we will put pi. Can somebody give me a good way to approximate pi as a ratio of 2 integers to 5 decimals? This is not a hard problem. It's okay if you're 6 decimals. You mean approximation pi to approximately 5 or 6 decimals. No. You know what answer I want. I'm sorry? 314,159 over 1,000,000. Right? That's a good approximation to pi. If I want a better approximation to pi, 2,600,5. Hey, I can get an arbitrarily good approximation to pi. So one of the things we like to do is we like to talk about the cost of an operation. So the bigger my numbers, the more expensive it is to work with them. So there was another suggestion that we should use pi is approximately 22/7. Anybody with a calculator want to tell me approximately what this is? It's about 3.1. Is it 428?
Yeah, 428.
I think it's 3.1428. Because I think 175. Okay. That is a pretty good approximation. I can remember 22/7 a lot better than I can remember 314,159,265 over 100 million. And when you're working with things on a computer, these are much smaller numbers. But this is a better approximation. So can I find a better approximation than 22/7, which is as good as this, but with a small denominator? So really, the cost is measured by the denominator size. Frequently, we'll measure it by like the log of the denominator, because the log of the denominator will be a good proxy for the number of digits. The bigger the denominator, the more expensive things are. Another way of looking at this is if I try to approximate my irrational with rationals, I'm going to get some error. I'm going to write the error as a function of the denominator. And what is wonderful about this is the error is very small relative to the denominator. Whereas in the other one, it's very different. So what we'll do now So we're going to look at alpha is irrational, and we want to look at alpha minus p over q. And we want to write this as less than or equal to some function of q. Or maybe I'll do it 1 over some function of q. The larger f of q is, the better. If I have 1 over q, that's not nearly as good as 1 over q squared, which is not nearly as good as 1 over q cubed. Because if it's 1 over q cubed, it means for a given denominator, I'm getting very close relative to that cost. So it's a huge question as to how well you can approximate irrationals by rationals. If you want to try to approximate rationals by rationals, well, you always want p and q to be relatively prime. There's going to be one perfect choice, and then everything else you can actually estimate exactly how far apart you will be. So what Dirichlet showed, there exists infinitely many relatively prime p and q such that alpha minus p over q is less than or equal to 1 over q squared. Hurwitz improved to less than or equal to 1 over the square root of 5 times q squared. Now again, earlier today when we were doing zombie infection, we talked about going from n squared to 1/2 n squared. And we said this is not really that big of a deal because you can go all the way down to n. That 50% improvement is not that big. We can't get lower than this. This is the best you can do. So this is a real improvement over Dirichlet. Getting a better constant there is significant. This leads to an interesting question. If this is the best you can do, which numbers are the hardest to approximate by rationals? Which ones have the largest possible error? So what is the most irrational number? Now again, there's many different notions of most irrational. Here, my notion is which is the hardest to approximate. Anybody want to guess as to what's the most irrational number? Oops, is this still on the board? Let me just erase this. Okay. Anybody want to guess what the most irrational number is? Pi, right? No. That was deliberately done to fool you. It's not pi. It is a number we've seen in this class. Or we've implicitly seen it. No, we've seen it. We've seen it. It involves the square root of 5. The golden ratio. 1 plus root 5 over 2 is the most irrational of all the most irrational of irrationals. It is the hardest to approximate by rationals. And one way to see this is something called the continued fraction expansion. If people are interested, let me know. It's continued fraction expansion. All of its digits are 1. The digits in a continued fraction expansion are non-negative integers. They're the smallest possible. One of the reasons we get good approximations to pi is it actually has large digits in its continued fraction expansion relatively quickly. Okay, so now what I want to do is I want to prove Dirichlet's theorem. Proof of Dirichlet's theorem. Again, I have to ask, what idea do you think we might want to use to prove Dirichlet? Monovariant is a good possibility, but no. Pigeonhole, right? So how would we use pigeonhole for this? We've got to find pigeons, and we have to find boxes. So we're going to do it in steps. We'll first find maybe m and n such that alpha minus m over n is less than or equal to 1 over n. Why am I starting like this? That's not what we're supposed to prove. We're supposed to prove things with squares. Why would I start with this? It's the same thing as we did when we did the mono invariants. It's the same thing we did when we did the spheres. Start with a simpler problem. Right? Try to find an easier case, understand that case, and build your intuition from that case. I want to eventually get to squares, fine. But let me start with something like this. I want to show that given, I can always find an m and n such that this is less than or equal to 1 over n. Maybe I'll even tell you, find an m such that this is less than, and now maybe n is given. I want to be within a certain tolerance. Any thoughts as to how I would do this? Yeah, so it seems natural that I want to split an interval into n parts. 0 to 1 over n, 1 to 2 over n, to 3 over n, to n minus 1 over n. Something like this. And what I want to say is that I've got to have two things in one of these intervals. So how many objects do I need? If I have n objects, will I have 2 in an interval? I need n plus 1. So we need n plus 1 pigeons to ensure 2 in an interval. So we have alpha. There might be an interesting way of rewriting alpha minus m over n is less than or equal to 1 over n. How could you rewrite that? And if you see the right way to rewrite this, this will help it with the problem. What's an equivalent inequality to this? Yeah, this is the same as n alpha minus m is less than or equal to 1. So if I fix n over here, I can keep increasing m, and as long as alpha is less than 1, this actually should work, right? So if I just keep increasing, so we're going to be very careful as to how we generalize. Without loss of generality, we can assume alpha is in the interval 0, 1. And then what I can do is I can just walk up in steps of size 1 over n, and eventually I've got to hit alpha. Alpha's got to be in one of these intervals, so if I walk up in steps of 1 over n, I'll hit it. What I want to do is I want to do things a little bit more generally, so what I'll do is find m and n, and now I'll make this like a big N over here. So now this would be less than or equal to maybe like n over n. So the idea of things to look at is maybe look at n alpha mod 1. And if I look at n alpha mod 1, because that's, if I choose m appropriately, I can choose m to be the integer part of n alpha. And when I subtract, that's going to be a decimal between 0 and 1. And then at least 2 of those decimals have to be in the same subinterval. And once they're in the same subinterval, I know their difference has to be at most 1 over n. So now I'd be changing from little n's to big N's, and basically looking at like the fractional part of n alpha. And at least 2 of them would have to be close. So again, I'm just trying to give you some motivation as to how we're going to prove this. By trying to look at the lower case, seeing what's going on there. We could also just walk in step sizes. So now what I want to do is I'll go and do the real thing. Find P and Q such that okay. So it's very similar to what we had before. So we have 0, 1 over q, 2 over q, 3 over q. I better stop because I have a Boston accent. Q minus 1 over q. And I'll let maybe x1 be alpha mod 1. x2 is 2 alpha mod 1. xn will be n alpha mod 1. So what this will mean is this is going to be alpha minus m1. This would be 2 alpha minus m2. This would be 3 alpha, this would be n alpha minus m. Right, for each one of them, there is a unique m associated. And if I go all the way down to x q plus 1, which would be q plus 1 alpha mod 1, which is q plus 1 alpha minus m q plus 1, I now have q plus 1 pigeons. Right? But I only have q boxes. So one box has to get 2 pigeons. Right? So now let's analyze the consequences of that. So without loss of generality, let's say n alpha minus m and a alpha minus b in the same subinterval. Then what do you know about their difference? Less than 1 over q. And for the record, the wireless is now working perfectly. So n alpha minus m minus a alpha minus b is less than or equal to 1 over q. So I could write this as n minus a alpha minus m minus b, yes, is less than or equal to 1 over q, right? So I get alpha minus m minus b over n minus a is less than or equal to 1 over n minus a times q. So let P be m minus b, let Q be n minus a, and what we've seen is we now get alpha minus P over Q is less than or equal to 1 over Q. That's pretty close to what we wanted, right? The only difference is we wanted little q squared. We have a little q and a big Q. Is this a problem? How big can little q be? What's the smallest little q could be? What's a lower bound for little q? One, right? We're not taking the same number. We have to take two different numbers. So the smallest little q could be, the smallest n minus a could be is 1. What's the largest it could be? What's the farthest apart they could be? So look at our pigeons. What's the extreme case? What's the furthest separation we could have in two elements? Not quite q minus 1. Close. You were looking at the things that are multiplying the alphas. Fortunately, we're not looking at the m's because we don't know what those are. We're looking at just 1, 2, 3, all the way up to q plus 1. What's the furthest apart you can be from 1, 2, 3 to q plus 1? Q. We could have the two extremes. So we know, worst case scenario, this difference is at most big Q. Thus 1 over big Q is less than or equal to 1 over little q. And so we might actually make a result a little bit worse, but we get alpha minus p over q is less than or equal to 1 over little q squared. And so we've just shown that we can approximate it as well as 1 over denominator squared. Now I said that we can do this infinitely often. What we do is we just let big Q go to infinity. If big Q goes to infinity, we can't use the same fraction again, right? Because let's say we have the fraction 22/7. There's going to be a certain difference between 22/7 and pi. If I make big Q sufficiently large, I know this difference has to be less than 1 over that, right? So I would have to get a new p and q. So by taking big Q larger, I will generate new values of p and q. So I will get infinitely many distinct. So get infinitely many by sending big Q to infinity. And that finishes the proof. So this is a really nice result from Dirichlet. So this is a good place to stop. I'll give you some additional reading to do on monovariance. And then if you want to do some of the challenge problems in terms of trying to push the stuff on Zeckendorf, just let me know. All right.